Hello, everybody. So this would be our last example for the buckling chapter and topic of buckling. So in the previous video, I showed you how we handle, columns with various end conditions and boundary conditions in a way. So I want to show you one more example here. So here we have this beam that is pinned at one end and A, and at the other end is being supported by this strut or rod BC, I called it here, or bar BC, which is made of steel, A992 steel, which is a stronger steel with a higher yield stress and ultimate stress. It's a solid shaft with a diameter of 50 millimeters. We want to find, see this load here, the intensity of the load is unknown. We want to find the maximum intensity of the load in newtons per meters without causing bar BC or this strut BC to buckle. And we want to use a factor of safety of 2 against buckling. So we want to be safe. So in a way, we want to reduce the weight of this guy and be safe. So how do we start this problem? Okay, there is one part that has to do with the drawing a free body diagram, which I did here. So we have the reactions at the pin A, AX, AY, and then obviously this guy is going to be in compression. So this reaction to that would be FBC shown here, right? So in a way, even though this bar is like that, so this strut BC or bar BC is in compression like that, okay? So over here, I took moment about A, and then I calculated FBC, right? So the moment of FBC about A is FBC times 6, right? And then you can change this guy to a 6W, right? Times 3 here, right? And so that's this guy. So FBC comes out to be 3W. So then I said, okay, let me go ahead for the calculation of the critical load. Let me calculate I. But remember, I for a circular section, which is the case here. So this strut has a cross section like this. I sub x and I sub y, or I with respect to any axis for that going through the center of the circle of the shaft is going to be the same thing. It's pi over 64 diameter to power 4. So that comes out to be equal to that. We also know that modulus of elasticity for steel is 200 gigapascal, and sigma yield is 345, which is much larger than your A36. A36 is about 250 megapascal, I believe. Anyways, I also calculated the area for later on for checking, the critical stress against yield. But anyways, I came back here and I said, okay, look, since this is pin connection, both ends are pinned, right? Then this would be the effective length of L or K of equal 1. Remember the equation? P critical is pi squared EI divided by KL squared, which is the effective length squared. So K is equal to 1. So we end up just getting L squared. So I plugged in all the values, the I, and the length is 3 meters, as you could see here, right? I calculated the critical load. So now this is our failure load, right? What is factor of safety definition? Factor of safety is failure load divided by allowable load. So what is the allowable load then? Failure load, which is this load that causes buckling, divided by factor of safety. So now we want to only have 33.65 kilonewtons. So the load that is allowed in this bar BC is going to be 33.65, and that's equal to what? This 3W here. So when I set them equal to one another, I calculate W in kilonewtons per meter. So based on a factor of safety of 2, that's the maximum distributed load that we can apply to this beam. Okay, and then just to check against the yield, since our critical stress, which is critical load divided by area, if you take this load, 67.3, and divide it by the area, which is given here, that comes out to be only 34 a little bit more than 34 megapascal, which is way below what the yield. Okay? So, as always, thanks for watching and listening. And this should conclude, this video should conclude the course, guys. I had a great semester, even though we had all these problems at the end with the, this pandemic. But hopefully everything will work out and you guys come back soon to school and continue with your education. Thanks again and see you soon.